Hi everyone, welcome back to this channel. This quick video I'm going to show you how to utilize the Keysight Signal Studio for pulse building, especially when you want to generate a pulse train on a PSG. So the PSG that you need to use is a vector type because it needs to run in arbitrary waveform generator. If you have that options, then you can utilize this software to build a pulse train as you wish. So a bit about this software, you can actually go to keysight.com and look for this software. So it's N7620B and you can try out for 30 days, and most of the signal generator from Keysight is able to utilize this software as long as you have the arbitrary waveform generator options. So this is how it looks like when you start that software. Just go through some of the setup that I have right now. This is how the setup look like, the hardware setup. So as you can see here, we have a PSG that will transmit a pulse train as we said using the pulse builder software, and then come out with the BNC splitter, and one of the BNC cable will connect to a PXA. So in the PXA, I'm going to show you later, it has both LTSA and also spec end mode. And the other end we connect to the new MXRB model, where we want to see the time domain pulse signal. So let's go back to the screen and I'm going to show you more on the setup. So this is how that scope look like on the screen. So I have a remote desktop to it, and the other one I want to show you is the PSA interface. So we have two remote desktop, MXRB model, the new model for time domain, and also FFT that you're seeing right now here, and we have a frequency domain using the PXA. So let's go into the software straight away. So before that, I have something running, so I just turn it off. So let's start from scratch again. Let's start with a new file, and I do not want to save anything that I've done. So this is how it looks like. So this is the pulse builder software, and I'll walk through quickly of things that you can change to build out your pulse train. So first of all, we have pulse library. So this is the part where you define how the pulse looks like. For example, if you want the pulse to have a pulse width of 2 microseconds, means that the on time for 2 microseconds. So this is where you change that. And rise time, fall time, it depends on whether you want to change the parameter. For now, I just stay with 39 nanoseconds. You can actually make it different rise and fall time depending on what you need or how you want to test your circuitry. And we have a pulse type, trapezoidal, rise, cosine, custom profile. This is where you can put in the CSV format and also custom IQ. So I can go through one by one and let you see how it looks like. And you can actually import the CSV format here. And we have a custom IQ. If you have an IQ file built up in CSV format, you can actually download to here. So we won't go through that. So that's for advanced user. So let's go to the default trapezoidal pulse time. So I set it to 2 microseconds, so the width is about 2.03 microseconds because it corresponds to the rise and fall time with a 6 dB bandwidth. So that's what I'm going to do now. And if you want to have modulations impart into the pulse, you can actually select from here, modulation type. And you can see that you can put in different type of modulations to be embedded into the pulse. But for our case, I'll select none. I can rename my pulse, rename, then I say it's 2 microsecond trapezoidal. So this is the first pulse that I created. So if you want to have another setup, like for example you want to have a wider pulse, so you can add into a new pulse. So we're going to use the pulse library here in the pattern library later. So this is where you set the fundamental pulse type that you want, then you recall it in the pattern library where you cascade different type of pulses one after another. So we go through that tab later. So let's create another one. Let's say we set it to 4 microsecond pulse width. So I can change the name first. Trapezoidal type. And I change this to 4 microsecond. Enter. Right now we have 2 different pulses that we can select in a pattern library. So you can add in as many as you want, and I do recommend to do a save so that you can reuse it, recall it after that. Let's go to pattern library. This is where you group the pulses per your test. For example, I want the 2 microseconds 50% and then followed by the 4 microseconds 50% duty cycle pulse. So these are where I group it, or I change the patterns that I want to create with all the pulses that I built in the pulse library. Again, you can rename this as you wish. You can rename here. And because my connections is using BNC cable, so there's a frequency limit to 1 gig. I will change that to 1 gig. Oh, sorry. Before we change anything here, we have to make sure that we have a physical connections to the PSG. So how do we connect this software to the PSG? The only information that you need is the IP address of the PSG, whether you connect dynamically using DHCP switches or static. It's up to you. As long as you are able to connect to a PC or computer that runs this software, then we click on this one, this icon, connect to instrument. So I have my PSG connected before this, but I can actually show you how to do you have a new connections. So once you click that, system config wizard will come up, then we click new, next. So this is where you type in your IP address. So once you key in the IP address, I normally will do a test I/O connections, just to ping and make sure that the instrument is connected. So it says test connection pass for that IP address. Then I click next. So when you see this signal generator connected, you're good to go. Then we click next. So this is where you put in the name for the system, the hardware system. So I have that PSG, I can type in, and a PSG name, it has to be unique. Then finish. This is how it looks like on the screen of the PSG. So by default, it has all, it's set to 10 gig minus 10. So according to the preset. Once we're happy with that connections, we can do this. Just change the frequency to 1 gig and amplitude. For now, we set it to -15. Enter. And RF output. Let's try and see whether the software is working with the PSG. So I will do this. Let's play pattern. Oh, because there's no signal. Alright, let's build in some signal. So how do we add in? You can either do this, new pattern item. So this is where the drop down, you can append or insert. Append is you will add to the lowest, starting from the lowest point. So it appends from the bottom. Insert is when you want to insert something in between 2 steps. So we're going to go through that later. So let's start with append. And this is where you can select the pulse from the pulse library. Remember we set both 2 microsecond and 4 microsecond trapezoidal type of pulse. So let's start with 2 microseconds. So remember the 2 microseconds is a pulse width. If you want to have a 50% duty cycle, we have to have 4 microseconds, 4.06. Just change that. 4.06 microseconds. So it becomes a 50% more or less duty cycle pulse. And we're going to go through the power scales and the frequency offset later. So we're going to build it step by step. So first of all, I have this on and I have built this. Let's download it to the PSG and let's play. There are 2 ways of doing it. One is just download, the other one is download and play. Just being lazy, I just click download and play. So you download the pulse pattern arbitrary memory and you will turn on that pulse. As you can see on the PXA LTSA mode, and this is how it looks like on the spectrum mode. Let's look at how it looks like on the scope. So I'm going to run and single it. So I turn on the marker just to measure the pulse information. So let's go through here. So as you can see, it's roughly 4 microseconds and it's a 50% duty cycle. So this is what we have set in the pulse builder. And something wrong with this. Let's close this. So I just refresh to the web server on the PSG, and this is how it looks like. So it's running on arbitrary options, running at 1 gig and minus 15 dBm. So it's exactly as what we are seeing. So again, this repeat doesn't show you much because it's just one pulse. Let's add on another pulse so that you can see the difference. This is where you can append. So you can right click, append. So let's say I want to make it to 1/3 of the duty cycle. So this is where I change it to 6.13. Again, this repetition interval is up to you how you want to change that. It will tell you that object length is 2.06. If you double it, it should be 4.12. If you triple it, it should be 6.18. If you want to go down to that detail. So it's 1/3 of it, and let's just repeat once. Same flat power and same as frequency carrier at 1 gig. Let's click on this, just download. And let's play the pattern. So again, you don't see much on the spectrum side because everything happens on the carrier frequency at 1 gig. Same as LTSA mode. Let's run this scope and single it. So if you remember, our first signal is 50% duty cycle, 2 microseconds pulse width. And then our second signal is this, 1/3. So you have roughly pulse period of 6.18 roughly here. And we want to see the pulse width. So again, it's about 2 microseconds. Let's say that's what we want. Let's build more on that so that you can see what other things that you can play around. Let's go back to pulse builder. Let's increase the repetition of this pulse. So let's say we want to set it to 4 times. And let's do it. Download and play. Let it run. It should be done. Let's play. I'll single it. So as you can see here. So again, this is the first pulse. And this is the second pulse. So because it repeats what 1, 2, 3, 4 times. So we have 1, 2, 3, 4. Then we repeat again on the first pulse. So everything looks exactly as what I want. Let's build more. Let's use the 4 microsecond pulse width. This is where you can select and insert in between index 1 and index 2. So as you can see, this was our second in line just now. So I managed to insert in between index 1 and index 3 right now. So by default it's a 20.3 microsecond. Let's change this to the 4 microsecond pulse width. And I want to make it to 50% also. So 50% of 4 microsecond, 4.06 is 8.12 microsecond. So I'll repeat 1 so that you can see how it looks like. So let's download and play. run and single it. So you can see that the 4 microseconds 50% signal is here. Let's move it here. So this is about 4 microseconds. This is about 4 microseconds and then 50%. Right, let's say this is what we want, and the next thing I want to do is we continue to build a few more. This exactly is what we are seeing on that time domain. So the next thing I want to do is to offset the frequency so that each pulse is happening at different frequency point. Frequency offset is relative to the center frequency over here. So currently it's 1 gig. And because our scale is so wide, the span in frequency domain, we want to make sure that we can see the difference in the frequency for each pulse. Let's change some of the parameters. So let's keep the first one at 0 Hz offset, the second one at -10 MHz. So the other one is +5 MHz. Right, let's do this. Download. And then play. Let's turn on the time domain, single it. So you don't see much different in this time domain, but you can see something changed here. You might ask why the amplitude is different. Partly it's because of the scope itself. So I'm going to turn on the PXA so that you can see something on. So as you can see, we have the center frequency 1 pulse, the other one is offset by 10, the other one is offset by +5 MHz. So we have 3 points here, and if you're interested to look at it in spec and mode, this is how it looks like. Okay, the next thing I want to show you is you can continue on with the same setup, add in more pulse, offset the frequency. What if you want each frequency point has different power level? Again, this power level is relative to the amplitude here, and we can change the power level. Let's say I want the center frequency to be lower by 10, and the last point I want it to be higher by 5. So once I'm happy with that, I can just download this and play after that. So you can see that the center frequency is off by -10. This is the one that we didn't change, it's still -20, and this is the one that we up it by 5 dB. So basically this is how you change the frequency offset and the amplitude offset. So before that, let me show you how you can save this state. Let's go to File, Save As. So this is a pulse building project file, and you can type in a name, then you can recall it anytime. So just bear with me, I'm going to do a few more additional pulse inside, and I'm going to speed up the video so that you can see how it looks like. By the way, you can actually stop the SIGGEN from turning off the RF power by clicking this stop. So I'm quite happy with this. I'm going to download and play. So as you can see, there's multiple points or pulses happening at the same time, and this is how it looks like in the RTSA mode. In frequency domain, this is how it looks like in spec and mode. It's hit and miss. And let's look at time domain. So as you can see, we have added a lot more of the signal, and some of the signal is not power the measurements. That's why you're not seeing on the FFT. Let's increase the time domain. So these are the combination of multiple pulses that we have, and I think I set up one too many. I might have a 20.3 milliseconds. Yep, it's just way too long for that. Let's change that to another 2.3. So the other one is repetition. Let's do it to 8.3. The other one, let's say, is 6.3. There we go. So you can see that changes on the amplitude, the frequency, and let's look at the LTSA. This is how it looks like in the spectrum mode. This is how it looks like on the time domain. So to summarize, first of all, you need to build pulse library. So this is where you define what is the pulse width for the library that you're going to use to build out the pattern. And then in the pattern library, this is where you define how many repetitions you want it to be, and what is the duty cycle, what is the frequency offset, what is the amplitude offset. One thing I forgot to mention is that, so as you can see right now, we have one pattern group, and all these pulses will go in sequence from index 1 to 5 and onwards. So if you want to create another group of patterns, you can add in this new pattern. So it will be independent from each other, pattern, new pattern 1 and new pattern 2. So I'm going to show you how it looks like. So let's say we set it to 1.1 gig so that you can see the difference. And amplitude, let's set it to -15. And I'm going to add in the pulse. So let's say this is the one that I want, and I add another one here, change it to 4, and I change it to smaller range. So some people might think that if we have multiple patterns here, it will go through from one to another, but in actual fact it doesn't. So I'm going to show you here. So this pattern 2, I'm downloading it right now, and let's play, and let's look at here. So center frequency I've changed to 1.1. Let's do it here. So it's 1.1 gig. So as you can see, that's a bit different now. So that's 1.1 gig. And as you can see here, pattern 1 is frequency at 1 gig, pattern 2 at 1.1 gig. If you want to go back to pattern 1, you have to re-download the pulse pattern and then let it run. So remember, we have 1.1 gig over here. Right, so that's just to prove to you that the pattern doesn't go in sequence. It's just a group of pulses that you create, and the only sequence that it runs is within that group. So this is basically what the pulse building software can do for you, especially for vector PSG, and for the modern MXG, you can use this to build out the pulse also. Hope this helped. Thanks for watching.